Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone, it's my pleasure to have Percy Diakonis here. Percy has been a great influence on many people here. In particular, a lot of my own research in the last 15 years has been dictated by the directions that Percy initiated 30 years ago. And now he's and as I said in the email, you can find him now in the list of the 20 most influential scientists today. Anyway, without further ado, today Percy will tell us about random walks on the Heisenberg group.
Thank you, Yuval. Hello, thanks for coming out. Let's see. First, there's a handout. So this is a no free lunch. You have to make sure each person gets one of these pieces of paper. Okay, that's the first thing. So this talk is about a homework problem I'm in the middle of. And I know better than to do that to you. You seem like nice people. So I'll try to explain to you why there's something in it, I hope, for you. The talk is joint work with Dan Bump, Angela Hicks, Laurent Miclo, and Harold Widom. And it's about, well, the Heisenberg group. So I'm going to call that group H. It's a very simple thing. It's the 3x3 matrices, upper triangular, and with entries x, y, z. And I'll write such a matrix as x, y, z. And so in particular, if I multiply two of them times x prime, y prime, z prime, well, that's x plus x prime. They just add above the diagonal, y plus y prime. And here, if you figure it out, it's z plus z prime plus xy prime. Just multiplying matrices. And x, y, and z, well, in physics, they're usually in R or in C. X, y, and z could be real numbers. They could be in number theory, where this is a big deal. They could be in the integers. For me, often they'll be in the integers mod n. But they could really be in any ring, and this all makes sense. The random walk on this group, the group is generated by this generating set I'll call S, which is 1, 0, 0, minus 1, 0, 0, symmetric random walk, 0, 1, 0, and 0, minus 1, 0. So random walk is you pick one of these two coordinates at random and you put plus or minus 1 there. You write down that matrix and then you multiply by it on the left. And so I'll try to motivate it in a second. But as math, if I say Q of G, G is a group element, is equal to 1/4 if G is contained in this set S and 0 otherwise. Okay, that's one step of the walk. And then Q star Q of G is convolution, Q of H times Q of GH inverse. Here's summed over H. So what's the chance of being at G after 2 steps? You had to have picked something your first step and then pick the thing that gets you to G your second step. And similarly, we have Q star K of G. The chance of being at G after K steps of the walk. And under no conditions, well, example of the kinds of theorems that people prove, several people in this room. If the entries are in the integers mod n, then, and if n is odd, because otherwise there's a parity problem, then q star k of g converges to the uniform distribution, u of g, which is equal to 1 over n cubed. So if you walk around on this group, you get to a random group element. Random group element means x, y, and z can be anything. And the rate of convergence is less than or equal to some constant e to the minus, I think it's 2 pi squared times k over n squared. And it's bigger than or equal to some other constant times the same thing, 2 pi squared k over n squared. And so this says, we say, order n squared steps are enough. If you go 10 n squared steps, if k is 10 n squared, this side is exponentially small. If k is a 10th n squared, this side is big, and everything is explicit. And so that's a typical theorem in the subject. How long do you have to walk? And if we're over z, for example, then random, this is an infinite group, and it's not abelian, and it's, I don't know, it's, so random walk isn't recurrent, you don't come back to 0, but you can ask how long do you, what does it look like? And, well, q star k I'll write the identity, 0, 0, 0, the chance, you can ask all kinds of questions, but what's the chance of being back at 0 after k steps? This is asymptotic to a constant over k squared, where c is equal to something, gamma of 1/4 squared divided by pi to the 5/2 times the square root of 2, if you wanted to know. Okay, so these are kinds of theorems that, that people prove. Now, this is a sort of generalish audience, and I want to tell you why I care about these things, and maybe a little bit why you might be interested in some of what's coming. So some motivation for this study, because that's...
Is it very obvious that it's transient?
No, it's not hard to see that it's transient, but it is transient. It's just, it's a theorem. I mean, it's a little theorem, but it's...
any group of more than quadratic growth is
right. Right, there are many ways to see it, but I'm just, but that would be a question you could ask, right? Is it transient or not? And you could ask about off diagonal, you can ask a lot of questions. And so my motivation for studying this problem, for giving this talk, is the following. The first is a funny question for you maybe, but not for me. Is this Fourier analysis good for anything? Actually useful. You'll understand that by the time I get through. Well, just to say a sentence about it, this is a random walk on a group, and you could try to study that using Fourier analysis, and it's hard to do, as you'll see. And I think that there are 8 proofs of this now, and none of them using Fourier analysis. And so, since this is the natural way to try it, well, you'll, I hope, understand. But that was my motivation. I just wanted to try to do one of these problems by Fourier analysis. The second motivation is about features of random walk, and I think this is a quite important topic for a lot of things. So I probably don't have to tell people in this audience that Markov chains are used for all kinds of computational tasks. And people like Yuval and I and other people in this room often study the question of how long do you have to run a Markov chain until it's close to its stationary distribution. Well, we have global kinds of results like this one. If I run the Markov chain n squared steps, then in this very strong total variation distance, it's close, which means for many, many questions, the answer you get from the uniform distribution and the answer you get from the random walk are close together. But you might not care about all aspects. You might only care about the aspect you care about. You're running this random walk to do a certain simulation problem. You don't care about all the other questions you might ask. How long do you have to run it to get your feature right? So this is an example where that comes into focus. So let me explain that. In this context. So the steps are, I'm going to pick elements of this set one at a time. So suppose the elements I pick are epsilon I, delta I. So that is, so this is either, 1, 0, minus 1, 0, 0, 1, 0, minus 1. Okay, those are the steps I pick. I won't write the last 0. And then my walk is, epsilon, well, I guess the way I'm doing it, epsilon k, delta k times epsilon k minus 1, delta k minus 1, epsilon 1, delta 1. That's my walk, and I'm going to multiply out, and I'm going to say that's equal to, say, xk, yk, zk. Now, it's very easy to see from the rules what, so here, xk is equal to epsilon 1 plus and so on plus epsilon k. And these epsilons are, 0 plus or minus 1. They're 0 with probability a half, and they're plus or minus 1 with probability a quarter. So this is just simple random walk on the integers mod n, if I'm in this context. And we know everything about how this behaves, right? That is, this behaves like the central limit theorem says, and if you think of the integers mod n as endpoints wrapped around a circle, it's doing random walk, and therefore it takes n squared steps to get random, and et cetera. But in particular, and the same for y, yk is equal to delta 1 plus and so on plus delta k. And the joint distribution of these two things follows the bivariate central limit theorem over z. And so when you multiply these matrices, what's here and here are like Gaussian random variables, and so we know everything about them. So let's look at this third coordinate. Yeah.
What are your pairs there?
So each time, so I'm using random variable notation. Each time I'm picking one of these four things, and each time the third coordinate's 0, so I'm forgetting about it. So this really could have been epsilon delta 0, okay, but I'm just forgetting the 0, okay, and they're random, okay. So epsilon delta is equal to 1, 0, or 0, 1, or minus 1, 0, or 0, minus 1, with probability a quarter each. So those are just the steps I'm picking each time, and then I'm multiplying them together. So there should really be a 0 following each thing, and then I'm multiplying them. So is that okay, Sarah? Okay, thank you. So what's the third coordinate? So here zk, I think it's this. It's epsilon 2 times delta 1 plus epsilon 3 times delta 1 plus delta 2 plus epsilon k times delta 1 plus and so on plus delta k minus 1. Okay, I think it's that. It's very easy to figure out what it is. I think it's that. And so, these epsilons and deltas, they're a little bit dependent. If epsilon I is +1, delta I is 0. Okay, they're a little bit dependent, but really, okay, so you can ask now, if you're a probabilist, forget about anything else, or any kind of a thinker about these kinds of things. How does this thing behave? What do I have to divide it by so that it has a non-trivial limit distribution? Here we know that xk divided by square root of k goes to normal with mean 0 and variance 1/2 or whatever it is. And what do I have to divide zk by? Well, what you can show is that you have to divide this by k. So here zk over k, that has a limit. This goes to a limiting random variable. This converges. This k gets large to a non-trivial limit. And because Yuval wrote a book about it, I'll just put it down. What's the limit? This goes to, I'll call it z infinity. This has a limit. This has a limit this way, weak limit. And where the z infinity is distributed as the integral from 0 to 1 of b1 of s db2 of s, where these are independent Brownian motions. And that's not very surprising. If I divide this by k, these are going to, if I divide this by root k, sorry, if I divide it by k, I put one of the root k's under these things, they all go to this goes to Brownian motion, and then this is a Riemann sum for this integral. It's not very hard. If you want to make math out of it, this is a martingale, and the martingale central limit theorem tells you it has a limit, and the limit is identifiable as that. And so that shows that that this third coordinate, this z coordinate, you see, these coordinates, it takes them, in order to go, they want to get random on the integers mod n. They have to go n squared steps in order to have a good chance of getting down to the bottom. This third coordinate is getting random much faster. So this shows that if k is of order a constant times n squared, zk is mod n is uniform if c is large. So this third coordinate is getting random much faster. So this is an example of features, and I think that it's an important thing to try to study. How long does it take parts of a random Walker or Markov chain to get random? Cn. You're right. I'm wrong. Thank you. Right. That's right. And C should be large and so forth. Anyway, those are so as a conjecture that we don't know how to prove, if instead of doing this with 3 by 3 matrices, if you do it with d by d matrices, and then you pick a coordinate just above the diagonal at random, and then you put plus or minus 1 there, and everything else is 0, just the analog of that. Yuval and Alan Sly had a beautiful paper showing that this takes, I think it's d squared, p squared steps on the whole group. But if you just look above the diagonal, it gets faster. And if you look on the second diagonal, it's faster still. And in the corner, it's very fast. I mean, just above the diagonal, one of these entries that's the same as what I just talked about gets random. So just above the diagonal, it takes p squared steps to get random. 2 above the diagonal, it takes p steps to get random. 3 above the diagonal, it takes p to the 2/3 steps to get random. And j above the diagonal, it takes p to the 2 over j steps to get random. And that's a conjecture. I can't prove that, but I'm pretty sure it's true. Okay, so that's a little bit of what I mean by features. I hope that's okay. And now I want to talk to you a little bit about what I mean by this question. So for a moment, let G be any group. G is any group, finite group, say. Group, like the Heisenberg group. And suppose that Q is a probability. Q of G is a probability on G. Then, and I define convolution just by this recipe, etc. So I do the random walk generated by Q. And you can ask, suppose that you don't have parity problems and that you're, living on a generating set and stuff like that. So suppose that Q star K of G converges to the uniform distribution. And then you can ask how fast it occurs. And one way in which I've studied those problems is to use Fourier analysis. So, so a representation of G is mapping that assigns group elements to matrices, GLV, with the property that rho of ST is equal to rho of S times rho of T. And so you assign matrices to group elements in such a way that products are preserved in that way. And the Fourier transform at a representation, Q hat at rho, is by definition the sum over G of Q of G, the weights times the matrices. So it's a matrix. The Fourier transform is a matrix. And as usual, Fourier transform takes convolution into product. So Q star Q hat at rho is equal to Q hat at rho squared. And the uniform distribution has the Q is uniform if U hat at rho, the Fourier transform of the uniform distribution is easily seen to be 0 if rho is non-trivial irreducible. Representation is called irreducible if you can't break the vector space up into two disjoint parts such that the representation only takes you into one part. Anyway, and is equal to 1 if rho is 1, the trivial representation. And so the way you can study this convergence to uniformity is by showing that high powers of this matrix converge to 0. And the upper bound lemma makes that precise. And it goes this way, 4 times the distance of Q star K to uniform. So this is this total variation distance is less than or equal to the sum over irreducible representations of the dimension of the representation. I'll try to explain this times the size of the matrix Q hat rho to the K, and this is squared, and this is the trace norm. So okay, that's and this V here, this V is d rho dimensional. So that's a bound that says if you have your hands on how fast these things go to 0, then you can bound this. So this is a completely general recipe, and this is perhaps perhaps the simplest non-commutative group. So if you like that kind of stuff, it's very natural. Why can't we do it on this group? What's wrong with that? What happens? What happens? Okay, and it's a famous hard problem, and I found out why, and you're going to hear why. Okay, that's but what kinds of things happen? So in order to talk about that, I have to tell you what the irreducible representations of the Heisenberg group are, and they're easy. So the representations of the Heisenberg group. And I'm going to tell you for the integers mod p, just it's not hard to say it for any group. If you want to know, ask me after for any. It's hard to say for any group. If it's not hard to say for any n, but it's a little more complicated. And let me tell you what they are when p is a prime. There are p squared one-dimensional representations. Characters. And there are p minus 1 p-dimensional representations. And one of the facts of life is that if you sum the squares of the irreducible representations, that sums to the size of the group. And p squared plus p minus 1 times p squared, the sum of squares of the irreducible is p cubed, right? P squared plus p minus 1 times p squared is p cubed. That's true. So, okay. So what are the representations? The one-dimensional representations, they're indexed by pairs AB, mod P, and so X, Y, Z. This is, so remember, a representation is a linear map. A one-dimensional representation is a linear map of a one-dimensional space into itself. That's just multiplying by a number. And this number here is e to the 2 pi I ax plus by over p. That's familiar. Those are the, you can see that if you multiply this and multiply these, the product is the product. It's okay. The p-dimensional representations, they go like this. They're on a vector space. So the vector space you can take all the same vector space. V is the set of all functions f, or column vectors f anyway. F from the integers mod p into C. Okay, so it's just, that's a space. And I just have to tell you how x, y, and z act. So here, rho, and there's only one parameter that comes up, C of x, 0, 0. Now, that's a linear map of this space into itself, so it has to take a function into another function. So it acts on the function f at the argument j as f of j plus x. So it just translates. Okay, that's okay. It just shifts. It's a cyclic shift, if you like. It just shifts the vector around. The next one, rho sub c of 0, y, 0. That's what underlies the Fourier transform. This acts on f at j as it's e to the 2 pi I c over n times y j as a multiplier times f of j. So it acts diagonally, and that's how it acts. And z acts rho sub c of 0, 0, z at f of j just acts even in simpler way. It's e to the 2 pi I c over n times z times f of j. Okay, so if you put it all together, rho sub c, c's a non-zero integer mod p of x, y, z. Well, it's something, it's e to the 2 pi I c over n times, they all combine, right? So y times, don't tell me, times j plus z times f of x plus j. This is acting on f of j. Okay, so those are the p-dimensional representations, and there's one for every non-zero. N is p. You all knew that, right? N is p. P. Okay. So that, so you can just check that they obey this rule, and it's not hard to check. So now, what does my Fourier transform become? So here, remember my Q is, I pick one of the two diagonal elements. They're plus or minus 1, and so here, Q hat rho sub AB, the Fourier transform, well, that's just you know, it's the Fourier transform with the one-dimensional representations. That's just, well, it's 1/2 cosine 2 pi a over p plus 1/2 cosine 2 pi b over p, 2 pi b over p. So it's just that's the Fourier transform, and Q hat at the p-dimensional representation. It's a matrix, and it's not a bad matrix. It's got a quarter in front. It's got ones just below the diagonal. It's got ones just above the diagonal. It's got a 1 here and a 1 here. And then on the diagonal is cosine 2 pi c j over p. 0 less than or equal to j less than p minus 1. Okay, so it's that matrix. And one of the jobs that there is going to be, which was new to me, is I had to get my hands on the eigenvalues of this matrix. And so if anybody's seen that matrix before or knows anything interesting about it, I'd be happy to hear about it. And so let's say what the job is in order to bound the Fourier transform. So I remember my job was to try to use this machine to bound the rate of convergence of the walk. So I have to bound. I have this calculus problem. So this is a matrix. It's a symmetric matrix. So it has real eigenvalues. The eigenvalues are beta 1 of c, beta 2 of c, beta, I don't know, p minus, well, p of c. They're real eigenvalues, some real eigenvalues. So, you know, if you write that thing out, I have to bound this. This should be rho, not rho. Not the trivial representation. So I have to bound this sum. This is a sum of two parts. The sum over a and b not equal to 0, 0 of, well, 1/2 cosine 2 pi a over p plus 1/2 cosine 2 pi b over p to the 2kth power. That's the sum over the one-dimensional representations, plus the sum of c equals 1 up to p minus 1 of, well, the dimension of the representation is p, and then the sum over j equals, well, 1 to p of beta sub beta of beta j of p to the 2kth power. This should have been, yeah, this is a norm squared, so this is the sum of squares of the eigenvalues. Okay, so just, I'm sorry, but I'm going to make you look at this for a second. I know it's not fun to look at anybody else's calculus, but I'm not going to do very much of it, and see if you can at least look and see what the job is. So one term in this sum is when a is 0 and b is 1. That's a term. So when a is 0, this is 1. Cosine of 0 is 1. This is 1/2 plus 1. Well, this is 1/2 plus 1/2 cosine 2 pi over p to the 2kth power. And that's one term in the sum. Well, cosine near 0 is 1 minus x squared. And so this is 1 minus 2 pi over p squared over 2 squared, something like that, to the 2kth power. And so in order to make this one term small, k has to be of order p squared. I mean, if k is 10 times p squared, this is like e to the minus 10. And so, okay, and then in the usual way, that's all the trouble. That is, all the other terms are smaller and they all add up, and you bound this sum by straightforward analysis, as long as, so k has to be of order p squared. So, good. I need to know about these numbers. And I need to know about them with some kind of reasonable exactitude. And I will show you, coming a little bit, beta j c is certainly less than or equal to 1 minus an explicit number over p. So something like that is true. And so this sum has p terms in it, and so you have to, and this sum has p terms in it, and so I need to choose k so large so that p terms, and then there's a p, so it's p cubed times 1 minus constant over p to the 2kth power. Well, if k is of order p squared, which I need to kill the linear terms, then this is tiny, so that doesn't cause any trouble. So sorry for making you look at this calculus, but that's what it would be involved if you were able to do that. So I was left with the problem of trying to bound the eigenvalues of these matrices. Now, by now I'm very good at bounding eigenvalues of matrices. And I just thought, it's a tridiagonal matrix. How bad can it be? What's that going to do? That's not going to cause any trouble. But then I realized that all the tools and tricks I know are in probability language and about stochastic matrices. Well, it shouldn't be so bad. This cosine can be negative. I'm sorry, cosine can be negative. So, and then the rows don't have a constant sum. And so I didn't know what to do. And I tried some things, and they didn't work. And so we tried some other things. And I want to tell you that, but before doing that, because I want to give you some more motivation. So why would anybody care about these matrices? It turns out they're famous matrices. So more motivation. So just to make it simple, let me try to take C to be 1. So m is equal to m1, and that has cosine 2 pi over p, or n, I'll make pn now, it doesn't matter, times j down the diagonal. So it's this matrix with just that down the diagonal. Okay, so those matrices come up. Here's one place they come up. Probably most people in this room know what the discrete Fourier transform is. So the discrete Fourier transform matrix Fn has, say, jkth entry e to the 2 pi I j k over n over square root of n if you want it to be a unitary matrix. So that's a n by n matrix. 0 less than or equal to j and k less than n. So, and there are teams of electrical engineers who want to know about the eigenvalues and eigenvectors of the discrete Fourier transform matrix. There's a fair-sized literature on that. Why do I care about it? Well, it turns out that, because of what the Heisenberg group does for a living, this matrix commutes with M. So, F inverse, I don't know, Fm is equal to Mf. So I'll put it here. And what that means is that they're both symmetric matrices. It means they're simultaneously diagonalizable. And I thought, I'm in luck. These engineers are going to know all about the eigenvalues of the discrete Fourier transform matrix, and therefore, since they're simultaneously diagonalizable, I'll know a lot about I'll know a basis for, I'll know how to diagonalize M. And, well, okay, that sounds good. It sounded good to me. But alas, not alas, but anyway, what's true, Gauss showed this, but the fast Fourier transform, it's its own inverse, right? So f to the 4th is the identity. And what that means is that the eigenvalues of this matrix are plus or minus 1 plus or minus I. That is, it's it's a unitary matrix, so it has eigenvalues which are roots of unity. And the dimension of the eigenspace are around n over 4 within 1. So I do get a reduction of m in, because m preserves the eigenspaces of the Fourier transform matrix, but it's not helpful. And there is a lot of work, as I said, in the engineering literature about various decompositions, eigenvalue decompositions for f, but because the bases are so non-unique, they weren't usefully related to m, and I couldn't use it. On the other hand, I now have very, very good approximate bases eigenvalue decompositions of m, and they do decompose the Fourier transform matrix, and that seems to be interesting. So that's one motivation, okay, for studying this matrix. A second motivation comes from physics, and so so this is Harper, Hofstaders, and martinis. Martinis, not martini. It's not a person, it's the alcohol. So there's a very large literature in solid state physics about periodic, the Schrodinger equation with periodic potentials. To just say a simple version of it, say on L2 of Z, square summable sequences of length C, the Schrodinger operator, it's just this operator with a periodic potential, takes, so I'll call it, I don't know, L of phi is an L2 function at J is equal to phi of J minus 1 plus phi of J plus 1 plus cosine theta J plus eta phi of J. So this is the analog of a second derivative operator, and they usually put a constant in here, a v. And if you want to compute anything, you discretize this operator and look at it mod n, and these are exactly my matrices. I mean, these are slight shifts, but that doesn't change anything. That is, these matrices, if you discretize it or take periodic boundary conditions, are my matrices. And there's enormous both applied, numerical, theoretical work on what's the spectrum of this operator. If you want to get famous, Arthur Avila just won the Fields Medal. One of his accomplishments that's listed is called the 10 martinis problem. That was a problem of Mark Katz, who in a talk of this sort said, well, I'll give 10 martinis to anyone who can solve this problem. And it was to show things about, this is an infinite operator, to show things about the absolute continuity of the spectral measure. And, well, people like Barry Simon and many other people have written lots and lots of papers. When this is a general parameter, when V is 2, which is the case that we're dealing with, this is called Harpers operator, or Doug Hofstaders worked on it in his thesis. And if you type in Hofstaders butterfly, you'll see lots and lots of references and looks at what the spectrum of the operator looks like. I won't try to say that more. I can. But there's a lot of interest in the eigenvalues of this matrix in the physics community, in the solid state community. So I won't say more about it unless asked. Okay, so I need to know about the eigenvalues of this matrix. So this is 2014. So take a look at the handout here. Well, this is this side with the pictures. So this is when m is 200 and the parameter a is c. So this is what's the biggest eigenvalue of that matrix when the parameter which I was calling C and is here called A, varies in its range. So what you can see is that, for example, when the parameter is 1, the eigenvalue is very close to 1, and I said it's 1 minus a constant over. No, the parameter across the x-axis is, let me write it down, thanks. The parameter, the matrix has cosine 2 pi. Well, I called it C times J over P, 0 less than or equal to J less than P minus 1, down the diagonal, and the parameter that's across the x-axis is C. Okay, so for each C, this is a matrix, and it has a top eigenvalue. And that's what's pictured here. Oh, P is 200, which isn't prime, but that doesn't matter. P is 200, sorry. P is N. So P is 200. So here it's called M. That's the size of the matrix, is 200. So what you can see is that the eigenvalues are pretty close to 1, and then they fall off. They're not monotone, unfortunately. They are symmetric, and that's not hard to show. And okay, that's good. Now, in order to use these bounds, I also need to know the smallest eigenvalue, the one that's closest to minus 1. And that's what the smallest eigenvalues look like. And these look like mirror images of one another, but unfortunately, that's just what they look like. They're approximately mirror images. Those two dots, for example, no, but they're not exactly mirror images, and so I also had to bound the smallest eigenvalues and so forth. And I'll come back and maybe talk about some of the eigenfunctions. This is the first eigenfunction. The eigenfunctions are localized, and they're very peaked around 0, and this v equals 2, which is the case we're in, is the critical case. If v is bigger than 2, then the eigenvectors are not localized, and when v is less than 2, they are localized, and here they also are localized. But which you can see they're mostly 0, but they're kind of very peaked around, very peaked around 1. Okay, so you can look, and then you have to prove something. Eventually, you have to prove something. I just looked on the table, and I won't, but it's a good time for a minute. So on showed me this. I can't hand it around because he'll kill me, but this is the Heisenberg group, a portion of the Heisenberg group with those generators. This is the Cayley graph of the Heisenberg group, and those of you who are interested can come up and take a look at it under inspection. So, okay, it's, I think, from a 3D printer, and I never saw such a thing, so I'm thrilled, thank you. But one can look. Okay, so I want to talk to you about the how you bound eigenvalues of non-stochastic matrices. And I'm afraid there's a joke about this. There's a joke about a physicist and a mathematician and, I don't know, somebody else, and, the point is the mathematician goes back to cases he knows and proves things by induction, right? So I'm going to go back to what I know. So I have this matrix, my matrix, and it's got cosine down the diagonal, so it's not positive. So I'm going to make it positive, and I'm going to make it substochastic. So I'm going to let M, I'll work with M1, I'll just call it M, but then I'll just add the identity. Now it turns out good to add a third the identity plus 2/3 of M. Okay, so once you add the identity and 2/3 of M, that makes everything non-negative and the row sums less between 0 and 1. So it has non-negative entries, and the row sums okay, so you can just easy to check that. And then I can make it into a stochastic matrix by just making it an absorbing Markov chain. So I'm now going to make a Markov chain K, which is like this. Here's infinity. Here's 0, 1, up to, well, n minus 1. And here's 1/3 the identity plus 2/3 m. And then here are some numbers which I'll call A0, A1, up to A n minus 1, which just make the rows sum up to 1. So let me try to explain that. Well, let's say what they are. Aj is equal to 1/3 times 1 minus 2/3 cosine 2 pi j over n. So it's just what you need to make the rows sum up to the identity, if I did it properly, to make the rows sum up to 1, if I did it properly. So what is this? This is a stochastic matrix. All the rows sum to 1. All the entries are non-negative. I added a site to the space, infinity, and this is a Markov chain, but if it hits infinity, it dies. So this is absorbing at infinity. If you hit infinity, you stay there. And the rest of the time, you could go to infinity. This is the chance of going from j to infinity. That's what this first row is. So, okay, I made the problem into something that's friendlier to me. It's a stochastic matrix now. Of course, this matrix is a stochastic matrix, so it has one eigenvalue, which is 1, namely, yes. And so if I can bound the second eigenvalue with this matrix, that'll be the top eigenvalue of this matrix, and then I'll be in business. So the way you do that, I'm going to call this set of states S, and S bar is S union infinity, in case that comes up. And I'm going to bound this by the minimax type principle, but I associate a quadratic form with this matrix, and it's a little bit tricky. It took quite a while to get it right. The quadratic form is a Dirichlet form, EFF. F is a vector, column vector, and it's just equal to this. It's 1/2 the sum over x and y contained in S bar of f of x minus f of y squared k of xy. K is this matrix. And this is a symmetric matrix, and this part is, well, let me write it down, u of x, where these are Dirichlet eigenfunctions. So f of infinity equals u of infinity is 0. But of course, k xy, kj infinity is positive. And so this, anyway, that's the quadratic form, which is useful and needed. And what you can show, the usual characterization of eigenvalues in terms of quadratic forms, shows that if we can find a bigger than 0, such that the L2 norm squared of any function f is less than or equal to a times EFF, this usual way of, the usual thing is the eigenvalue is the quadratic form divided by the length of the vector, and so then that ratio will be bigger than 1 over a. That is equivalent to, or implies anyway, that that the top eigenvalue of this matrix, which I'll call beta, is less than or equal to 1 minus 1 over a. So if I can bound the quadratic form, I can get a bound on the eigenvalue I want. And now I use this path method, but here it's a little bit different because of this infinity, and that's a new thought to me. We need paths, and for gamma x, which take any x and connect it to infinity. So this is x naught, which is x, then x1, x2, up to xd, which is infinity. And they have to be paths in the graph. That is, I need k of xi minus 1 xi to be bigger than 0. So I need paths connecting any x to infinity. Okay? And the way we use that is we write f of x as, well, f of x minus f of x1 plus f of x1 minus f of x2, etc., plus f of x d minus 1 minus f of xd. The point being everything cancels out, and this is 0. So that's just an identity. And then use Cauchy-Schwarz. That's less than or equal to the length of the path, the number of terms in the sum, times the sum of squares, f of xi minus 1, I don't know, minus f of xi squared. And then that's like this, and then you fool around in the way that is a standard way of fooling around. Read Yuval's book with David Levin and Elizabeth Wilmer, Path Arguments, and the bottom line is, using the geometry of the graph, you wind up proving this kind of a bound. You can take A, this A which works here, to be the maximum over edges xy, where x is in S and y is in S, could be infinity, that has to be allowed. 1 over k of xy, this chance of this path, times the sum over z, such that xy is contained in the path of associated to z and the length of the path. So that you can prove that kind of a bound. And then, so you want A to be small, turns out. In order for this bound to be useful, you want A to be small. And so A will be small if you can choose paths in the graph which take you from x to infinity with the following property. None of these things should be too small. So that's important. And you shouldn't have too many paths that use a given edge, because you don't want the sum to be too big. And so that's a kind of thing that we do as combinatorialists, and I'll just say a sentence about that, but then I'll just stop. Here's infinity. Lots of things connect to infinity. You can go from any j to infinity. So there's infinity, and here's, here are these points, 1 up to n minus 1. And if you start here at the beginning, this thing is very close to 0. It's 1 minus cosine, right? I probably have these numbers wrong, but this thing is very close to 0, so you don't want to do that. So what you do is you connect points to infinity by going from here over into where it's non-zero, and then up to infinity. And this point you go to here, and then up to infinity. This point you go to here and up to infinity. You do the same in the opposite direction. You have to choose a breakpoint, and you go here, and then here, and then here, and then up to infinity. Points in the middle you connect directly to infinity. And what you can see if you choose paths that way and do the combinatorics, this isn't too small, and therefore 1 over it isn't too big, and this isn't not, at most 4 paths use an edge, and the lengths of the paths are not too long, and so you can control this. If you do this carefully, you get that you can take A to be of order a constant times, for this case, constant times 1 over p to the 4/3. Now, that's more than enough for the eigenvalue bound. This is A, so that, oh, yes, c times p to the 4/3. And so the eigenvalue bound, you get beta is less than or equal to 1 minus some constant over p to the 4/3. And that's not what I used before, but it's more than enough to do the job. So I'm going to stop here except to say time flies, and it is about time and over time. We actually know for these matrices, I actually know what the top eigenvalues are, at least in the corners. And so actually beta is equal to 1 minus pi over 2 p plus big O 1 over p squared. And actually if I put in a c, it's c over p, as long as c is small, c fixed. So I was able, our crew was able to relate the eigenvalues of this matrix to the eigenvalues of the harmonic oscillator, which are very well known, and use that relationship in order to bound these eigenvalues. Unfortunately, I need to know this not only for C fixed, I need to know it for all C. And these cruder geometric arguments work great. They don't give quite as precise results, but they do give good answers. So I want to finish by just saying I started on this talk for two reasons. I wanted to know, is Fourier analysis useful, and if not, why not? And I wanted to know about the distribution of the center argument. Well, I can't answer. This is pretty hard work, is all I'll say. We really have 7 proofs of the fact that n-squared steps are necessary and sufficient for random walk on the Heisenberg group. So, did I need to do it this way? No, is the answer. But still, it shows, what the difficulty is. Having done this work, it is important to say there are lots of other groups where the Fourier transform has exactly this form. And so, more or less, any class 2 nilpotent group, the Fourier transform, the high-dimensional Fourier transforms have this form. And so knowing about the eigenvalues of these matrices, there are a bunch of other random walks, some of which our previous techniques didn't apply to, that we can do well. It is also worth saying that these sharp eigenvalue bounds are much better than what ergodic theorists and Arthur Avila got on the problems that they care about. They didn't actually care so much about the extreme eigenvalues, although they did care about them, and they got we got much sharper bounds, and so that's good. So I hope that you know what I was up to trying to do my work on the Heisenberg group, and I hope that was instructive for you sometime. Thank you.
Question?
So does try to expand this a little bit to the other upper triangular matrix groups, all ones in the diagonal, integers above, or
yeah, Sarah was the editor for our super character paper. Bless you. Yeah, I didn't try. We just decided I was going to do this one, and I didn't know. I mean, I will eventually try. But one of the problems is for the group of n by n upper triangular matrices, nobody knows what the irreducibles are, and in some sense, you can prove that nobody will ever know. They're wild problems. And for this case, I said, well, here are the irreducibles: 4 by 4, okay; 5 by 5, okay; 6 by 6, and then it stops. I mean, nobody knows what the irreducibles are, I think, for 7 by 7. And we don't know the characters, we don't know the conjugacy classes. So we did manage to make new and better and easier to use super character theories using these ideas, and so I would like to do more about that. But I just decided I wanted to do this problem. How hard could it be? It's a tridiagonal matrix. It shouldn't be so bad. Well, okay, I have scars to prove it. It wasn't so much fun.
What do you mean by you can prove that you can't find the counterexample?
You can't find the counterexample? That's a good question. So let's see if I can explain that. So the claim is that these are these groups U and P, FP, which are ones on the diagonal, star in FP. You know, what I claim is that I'm going to try to convince you that there is a proof that you can't describe the conjugacy classes. Now, of course, for any finite n, it's a finite problem, and leave me alone. Okay, but I mean, there's not, you know, like the conjugacy classes of the symmetric group, I'll explain as a math thing, but the conjugacy classes of the symmetric group are indexed by partitions, and that's okay. Right? For GLN, we know. These are nice groups. They're the CeLO-P subgroups of GLN. I mean, they're not bad groups. Okay, so let's see. I proved that if you had a nice description of the conjugacy classes by a bijection, you'd have a nice description of what are called wild quivers. So a quiver is just a collection. It's a directed graph. I don't know. Okay, and a representation of a quiver is a vector space at each place and at each vertex, and a linear map. Nothing has to commute, just okay. Two representations are called equivalent if you can change bases and make the linear maps actually the same. Okay, so they're equivalent up to change of basis. And a problem is classify quivers with a given, you know, representations of quivers. So these are familiar problems if you have one dot and an arrow leading into it. That's classify linear maps of a vector space into itself up to change of basis. Okay, that's the rational canonical form. That's good. Okay, we know what that is. Here. Two dots and an arrow going from. That's, you have two matrices and you have a linear map and you're allowed to change bases arbitrarily. There's only one invariant, which is the rank. Okay, but still, that's nice. Okay, quivers in which the representation type is indexed by an integer, like the rank, are called finite type. Quivers in which the representations are indexed by a finite collection of real parameters or complex parameters, those are called, what are they called? Not finite type, tame. They're tame. And there's a trichotomy theorem which says any quiver is a finite type, tame, or wild. Just so you see there's some content that sounds crazy, but a quiver is a finite type if and only if it's an orientation of a Dinkin diagram. That's a nice theorem. That's Gabriel's theorem. Okay. So I showed that if you had a description of the conjugacy classes, you would have a nice description of a wild quiver, this one, two arrows. This is classify pairs of linear maps from a vector space into another vector space up to change of basis. So that's, you have a pair of matrices, and say you have a pair of matrices, and you want to classify them up to change of bases. And there's no, okay, now there's a theorem that says if you had a nice description of wild quivers, any wild quiver, then there's an unsolvable word problem that you could solve. So it's much worse than PNP. It's, it's up there. Right? So the complexity. So now, to try to get a finite quantifiable version of that, I'd love to do that. And I keep trying to find a tame model theorist. The theorem I just told you about, that there's this equivalence class, it's on page 300 of a book called Modules and Model Theory. And unfortunately, there are 299 pages before that theorem. Okay. But there is a theorem that says that if you had a nice description of wild quivers, you have a... And here, it's very easy to say what you do. Given a matrix, you embed two big blocks in it. Conjugation, describing the conjugacy classes of such a matrix, you can easily see is equivalent to classifying pairs of maps from one space to another. So I hope that gives a flavor for it. And but if you can ever make more sense out of it, I did spend a week with Katrin Tent, who's a model theorist, trying to make a quantifiable version of it. I don't. Right, but in some sense or other, you can prove it. I have a paper with Richard Stanley and Arias Castro, which is called Random Walk on the Upper Triangular Matrices, Mod P, and it has all this literature and the proofs and everything. Everything's written down. It's about 10 years ago. But we'll never get out of here. We don't know. I'll answer any question.
we have the room for 7 more minutes. But so this group is obtained from a group on the, on over Z by taking out all the coordinates small m. So you could use estimates from Euclidean space, like every cell of cost, and then take that.
Right, that's one of the proofs. And in order to go from infinite down to finite, we needed Harnack inequalities, but they exist. I mean, and actually, this guy Alexopoulos has this for any nilpotent, discrete nilpotent group. He has, the right Harnack inequality. So that's one way of doing it. Now that's bringing in a lot of hard work. It just seemed to me, here's this poor little group, Fourier analysis, it's tri-diagonal matrices. How bad should it be? I mean, that's what I was trying to do. It's an exercise. I said, it's an exercise. I was trying to do an exercise. And it got me, wham. I'll show you. So your proof with Alan Sly, you did n by n. I've forgotten whether you did general P, but probably did, that is, Yuval has a beautiful proof of the rate of convergence for n by n matrices, showing that, P squared is enough, based on a very clever foundation. But I mean, there are really a lot of different proofs. This is just, it's a straightforward approach. You could try it on any group. The other cases, there are special tricks. We're using structure, and I wanted to try it. It was really a homework problem, which turned into 3 papers. That's what else can I say?
Okay. Any other comments or questions? If not, let's thank Percy again.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.